Alrighty, so today we're going to try and finish up particle filtering. And let's start with the recap, and then we can get into the weeds of particle filtering. So the premise of particle filtering, if you remember, was that when we need to instantiate our belief distribution, if you have a multi-dimensional continuous distribution and you discretize per dimension, you have a lot of empty space. So we changed our data structure to not just have k to the n bins, but rather have a list of particles. So you only keep track of things where there is likelihood, right? And we said that that's going to scale better with memory and compute, right? So that scales exponentially, and this is hopefully not going to scale exponentially. Like in the worst case, it'll scale exponentially, but in most cases, it'll be a lot better. That's the premise of the particle filter. And so if we look back at our Bayesian filter, right, like you go from belief to belief bar, and then belief bar to the belief at the next time step, right? So then in both of these updates, you're just going to represent our belief by a set of particles, right? So, in our toy examples, we have represented them by tables. In the particle filter, we're going to represent belief not by some explicit probability distribution, not by a table, but instead by a set of particles, right? A set of particles is a list of states, right? We're going to have a list of states at belief xt minus 1. We're going to do our particle filter. It's going to give us a list of states at xt and or at time step t. And that's going to be our belief, right? And our job is to just figure out how to change that list to that list, right? And so kind of pictorially, the way you're going to represent a belief state is you're just going to have like a collection of particles, higher where there's more likelihood, or more particles where there's more likelihood, less particles where there's less likelihood. Okay? Just intuitive. Let's see. I'm going to, just to give you some intuition, I'm going to fast forward a lot. But like the way that a particle filter kind of looks is something like this. You start with particles everywhere, right? And then you like take measurements, you'll do movement, and you'll see like the particles will collapse, right? So that's kind of your belief. So intuitively, you can think of like, that was my initial belief state, right? It's pretty uniform. And then you move, you take measurements, you move, you take measurements, you can see that the particles move, right? And the particles move to cluster around your belief. So every step you see the particles move, and they're like, some are disappearing, some are appearing, right? But like, you're quickly concentrating around where you actually are. And so that's the way you want your particle filter to behave. And so just remember, like each of these are like actual states, like X, Y, theta for your car. Okay. That's how it kind of looks pictorially. So the two updates we care about are the motion update, the dynamics update, and the measurement update or the correction step, right? And so we care about this integral to the dynamics model. We're going to take belief at xt minus 1, multiply by the dynamics model and integrate. And the measurement update is multiply by the measurement likelihood, right? Be at zt given xt, and then renormalize. And so we're going to try, it's easy to do the table, because that's just the sum, and that's just a multiply and like average over a column. But we're going to figure out how to do this for particles, right? Because particles are not tables. Okay, so again, to kind of make this pictorial, this is our initial distribution of particles. After a movement step where you take an action, your distribution of particles looks something like this, right? So you took a movement step, your particles all move to the right, and so you push the particles forward according to the dynamics. And so the movement step in a particle filter is very simple. The measurement step is more of a pain. Movement step is just saying like take your list of states, push them forward through your dynamics models, right? If you have your dynamics model, P of xt given xt minus 1 ut, right? Take your list of S1, S2, S3. For each of them, stick it in as xt minus 1. Take the actual action that you took, sample a new state, and that is going to go into your new list, right? And so you'll have S1, S2, S3, and that'll translate into some S1 prime, S2 prime, S3 prime, right? And so there's nothing really fancy to do. You're just going to take your list of states, stick it into your dynamics model, sample a new state that gives you a new list of states, right? And so if you want to go from belief to belief bar, There's no fancy integrals to do. There's no fancy reweighting to do. You just take each particle, put sample from the dynamics model conditioned on that particle. That is your new list of states. Okay, so pictorially, you can kind of think of this. This was your list of states. You pushed it forward with the dynamics model, which means it's called the function on with those states as the input. They give you a new list of states, right? But the nice thing is you don't actually force the dynamics model to have any particular form, right? You're saying that the dynamics model can be non-linear, it can be non-Gaussian. Like I don't care if the dynamics model has a particular form. It just needs to be something I can like sample from, right? So the important thing is that you need to be able to sample from it. And as long as I can sample from it, I'm good, right? And so that's the important thing about the motion step. Any questions about this? Does it make sense? Does it not make sense? And then we'll try a different explanation. Ish? Yeah? Okay. So on Monday we'll try to cover the Kalman filter, which is an instantiation of this with a Gaussian. And the nice thing about the particle filter compared to something like a Kalman filter is that it doesn't assume anything is Gaussian. It doesn't assume anything is linear. It's just like, I just need to be able to push forward and sample, right? And so like works nicely on really complicated nonlinear dynamics. So anytime you have complicated dynamics or complicated measurement model, particle filters are great. Because it's like all based on sampling. It's based on compute rather than a particular form. Okay. Great. So that's the motion step, right? And then we were talking about the measurement step, right? So in the measurement step, you're gonna try and take your belief, you're gonna try and multiply it by the likelihood of P of ZT given XT, and you're going to renormalize, right? But it's not, when it's a table, it's pretty clear what to do because you literally have a number for belief bar. You literally have a number for P of ZT given XT, right? You just multiply those two numbers and renormalize. Right? You just multiply the tables and then you renormalize. If you remember our example with the robot opening and closing doors, right? You just took those numbers, you multiplied, yeah, you renormalized. But now my belief bar, I don't actually have numbers. I just have a list of particles, right? So it's not super obvious how to do the measurement step when I have a list of particles because I don't have the probabilities. I only have samples from belief bar. I don't actually know the like number, which is the probability. And so what makes the measurement step difficult in the particle filter is that you don't actually know the numerical value of belief bar. You don't have a closed form probability distribution. Whereas in this step, I don't actually need a closed form. I just like need to be able to sample. But in the measurement step, I am trying to like multiply this value by this value. But unless I know the value, like what do I multiply with? That's what makes the particle filter measurement step hard. Okay. And so our job is going to be to figure out how to still do this without requiring us to get an actual value for the likelihood. Okay, so the trick in a particle filter is that you're going to like introduce another element to your data structure. And so we initially just had a list of states. Now we're going to have a list of states and weights for every particle, right? So your particle filter is going to have essentially two lists. One is going to be, S1, 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 S2, S50, whatever. And you're going to have like W1, W2, W3, W4, right? And so like each state is paired with a weight, right? So it's like two lists, one which is a set of states, one which is a set of weights, right? And every particle is going to be paired with a weight, and we're going to like essentially incorporate the measurement update into the weights, right? Because we don't exactly know how to move around the states, but we're going to introduce these weights. We're going to incorporate the measurement update into the weights, and then I'll show you how we can like use it for all the other things we care about. Okay, and the way we're going to compute the weights is pretty natural. You're going to say, I'm going to take for every particle that I have, let's say my particles were like S1, S2, S2, S4, right? For every particle, and let's say I got a measurement in the world. Let's say I got a measurement Z in the world, right? For every particle, I'm going to compute P of Z given S1, P of Z given S2, P of Z given S2, P of Z given S4, right? This is going to give me four numbers, and then I'm going to normalize those numbers, right? And so I'm going to have four different numbers. I'm going to renormalize them, and that's going to give me my weights, right? And so um, it's essentially the same thing as like taking your measurement model and renormalizing, but we're just going to do that on these weights, right? So now we're going to represent our belief distribution by this combination of a list of states and weights for every state, right? And so the next thing we're going to show is that's not super arbitrary. It's not just like a random thing to do. And that like when you have a weighted set of particles, you can still use it to do all the things we want to do with the particle filter. Like if you remember the motivation from last time, the goal of having a belief is to compute an expectation, right? You want to compute averages. And the point we're going to make is that when you have a weighted set of particles, you can still compute averages. And that's really what you want, right? Okay. So everyone with me so far? Like, just to recap, we started with a set of states. We said belief is a set of states, but it's hard to incorporate the measurement. So we added weights, and we said the weights at every step are going to be computed by taking the likelihood of Z given X and then dividing by the sum, right? So this is just normalized. Right? The weights will always sum up to 1. Good. Like the one that's a big sense kind of right. Yeah. Correct. We're going to do a resampling process in like 10 slides, and that'll do what you're just talking about. That'll help you collapse the things that didn't happen. Great question. Okay, so the next section is going to be a little more mathy, but really what we're trying to show is like, the purpose of having a belief state represented as a set of particles is to compute an expectation. Compute expectation with respect to belief of some function f. Right? If you remember, we said that if f was x, then it would be the mean position. If f was if f was an indicator for collision, this would be the average probability of collision. If f was a cost to go, this would be the average cost to go, right? And so the reason you have a probability distribution is to compute an average. And so what we're going to show, what we showed last class, was that if I represent things with a list of particles, I can use this Monte Carlo sampling. So I just like, let's say I had a list of particles S1 to Sk. And if I had some function f I'm trying to take the average of, I just evaluate f of S1, f of S2, f of S3 till f of Sk, and then I average them, right? And that gives me the expectation, right? So whenever I have a list of particles, unweighted particles, I just like do f at each of those particles and average them, and that gives me the expectation. But now I've changed the data structure. I've said like, I'm going to have not just a list of particles, I'm going to have a list of S1 to Sk, and I'm going to have weights W1 to Wk, right? And so I want to make sure the same logic holds. I want to make sure I can still compute averages with the weights, right? And so I'm going to take a little bit of a detour, but we're going to come back. And we're going to introduce an idea called importance sampling. Have you all heard of importance sampling? Anyone heard of importance sampling? New-ish? Okay. So the premise of importance sampling is that I have a distribution P of X I want to sample from. Like I want to take the expectation under some hard distribution P of X, but I like can't draw samples from P of X. But instead I have samples from some simpler distribution Q of X. Like how do I take an expectation under P of X when I only have samples under Q of X? So the premise of importance sampling is I want to compute this number, okay? But I only have the ability to sample from Q of X. It's almost magical, right? Like if I wanted to compute this thing, right? Like if I could sample from P of X, I would just draw a bunch of X's, evaluate F, and then average them, right? So I would just say, if I could sample X from P of X, I just draw a bunch of X1, X2 till Xk. I evaluate F on each of them, and I average them, right? That gives me the expectation. But if I cannot draw samples from P of X, I can only draw samples from Q of X. The question is, how do I compute this expectation, right? And the reason this is going to be irrelevant for our particle filter discussion is we're going to show this like weighted particle filter thing is kind of like an instantiation of this particular problem. Okay. So let's deal with the abstract problem first, and then we'll bring it back to the particle filter. Okay. So before I give you the solution, let's solicit some suggestions, right? So the problem is I want to compute expectation P of x, f of x, and I only have samples x1 to xn from Q of x. Right? So I can evaluate if I like know what P of x is. I can get a number for given an x, I can give you P of x. Given an x, I can give you Q of x, but I cannot draw samples from P of x. So how might we compute this expectation? Any ideas? Except you who knows it for example. um, how could we try doing this? Any ideas? Let's just make an attempt. Any thoughts? Okay, let's keep going, and I'll give you some information. So the idea is basically reweighting, right? So let's say you had samples from an easy distribution. Normally, when you do Monte Carlo estimation, right, you say that you draw x1 to xk from some distribution, let's say P of x. And then if you want to get expectation under P of x, right, what you do is you say, hey, every one of these samples has equal weight, right? I'm going to say compute f of x1, f of x2, f of x3, and then I'm going to just like sum them up and then average them, right? Each one of them has equal weight. But in important sampling, the important thing is I do not have samples from P. I instead have samples for Q. And the trick is that rather than giving each one of them equal weight, I'm going to give them weight that depends on how similar P and Q are, right? So things that are sampled from Q but are really unlikely under P will have low weight. Things that are sampled under Q but are really likely under P will have high weight, right? And so the trick is we're going to take samples from Q, but we're just going to reweight the average, not just have an unweighted average, we're going to have a reweighted average. Okay, so let's say this was our target distribution P of x. We don't know how to sample from it. These are the samples that we want, but we can't get them. Right? Instead, we have an easier distribution Q of x that we can get samples from. And what we want to do is we want to compute the expectation under P of x. And the way we're going to do it is we're going to do it through reweighting, right? And so let's do a little bit of derivation. The easy way to get to the derivation is like, let's define what an expectation is, right? An expectation is an average. So in a discrete case, it's a sum. In a continuous case, it's an integral, right? But it's sum P of x, fx, right? An expectation with respect to some probability distribution P of x of some variable f of x or some random variable f of x is sum P of x, f of x, right? That's the definition of expectation. So the next thing we're going to do is we're just going to do really simple multiply and divide by Q of x, right? And so this is just multiplying by 1. And then we're just going to group some of the terms together. So we're just going to group these two terms together. Okay? So when you group those two terms together, you can rewrite this as Q of x times P over Q times F. Right? We just multiplied and divided by Q, and then we just rearrange the terms a little bit. But the nice thing now is that you can think of like if an expectation with respect to some probability distribution of f is sum P of x, f of x, like this thing also looks like an expectation, but under Q of x, right? So if you think of this as like, this is the, like in this case, this is the probability P of x. This is the thing you're integrating, right? The second thing is the thing you're integrating. So this is the probability, this is the thing you're summing up. In this case, this is the probability, and this is the thing you're summing up, right? And so you can rewrite this last term as essentially an expectation under Q of P over Q times F. right? And so essentially it's saying that like, hey, I had this expectation under P initially. I can rewrite an expectation under P as an expectation under Q, just reweighted by P over Q. Right? So it kind of matches the intuition we had earlier. Like you just reweight. It's still now the way to do this, you take a bunch of samples, you compute this value, and then you average this stuff. But it's like no longer equal weights, it's weighted by P over Q. The things where P is high will be weighted high, and things where P is low will be weighted low, right? Does that make sense? So the important thing is like what we're trying to do is we're trying to like convert an unweighted average under one distribution to a weighted average under another distribution. Like the place where this is actually used is in like scientific experiments and so on, where you have like these functions that are really hard to sample from. Like like the probability of a cell multiplying or something is like really complicated function. It's really hard to like sample from that distribution. You often have an unnormalized probability, but you can compute two unnormalized probabilities. That's in practice, that's when you really use importance sampling. But you also will use it in the particle filter. Okay, but the important thing for you all to take away here is that like this this expectation can now be computed by taking k samples from this distribution Q, computing this P over Q ratio, which we're going to call our importance weight, right? And then just like averaging in a weighted way rather than unweighted way. Okay, so abstractly, we had this expectation. It's easy to compute Monte Carlo. You just draw a bunch of samples and average them. If I didn't have samples from P, had samples from Q, I can still do the averaging. I just have to reweight it by P over Q. Questions? Does that make sense? I still haven't told you why that's important, but yeah.
Like is the probability of next time here for the
Under P. That's right. That's right. It's your probability density function or probability mass function. So it's like you literally compute a scalar number. Okay. When is this not going to work? Like, are there conditions where this like importance weighting thing doesn't work? Like, just look at this P over Q thing. When does this thing become degenerate?
like Q is 0.
When Q is 0, yeah. If Q is 0, but P is not 0, that's a problem, right? And so essentially, if you like the intuitive way to think about this is imagine you had this distribution and this distribution. Like none of, and then like they had no support overlapping. Like they had no, like there's zero likelihood that overlaps between this guy and this guy. Like no reweighting is useful, right? And so the condition for importance sampling to work is that P of X and Q of X need to have overlapping support. So support is like the range of values over which the probability is greater than 0, right? And so if both have 0 in the same places, it's fine. If one has 0 and not the other doesn't, then you're in trouble, right? Because this thing is going to go to infinity. You really don't want anything to go to infinity. Okay. So all that importance sampling says is that if you have expectation under P, I can do it through Q, just through reweighting. And the intuition is we're going to show that like this weighted particle filter is essentially an example of importance weighting, importance sampling. Okay, so we have this distribution. It's our belief at the next time step, right? Let's say that is P. And let's say we have let's say we have our distribution belief bar, right? So it's like before you incorporated the measurement, this is from belief, you incorporated the action and the measurement, right? So the distribution you want to sample from is belief. And the distribution you want to compute expectation under is belief. But I don't have samples from belief. I only have samples from belief bar, right? So if you remember the motion step, I took my list of states, right? And then I went from one list of states to another list of states. So I have a set of samples from belief bar, but I don't have a list of samples from belief, right? And our goal is to say, if I only have a list of samples from belief bar, and I want to do expectations under belief, how do I do it, right? And so to kind of cast into our abstract framework, belief is P, belief bar is Q, right? So remember, with belief bar, I like have a list of states. I just took my previous states, I pushed them forward. I have a list of states, which means I have a list of samples from belief bar. But from belief bar to belief, I don't know how to get samples, right? So the question is, how do I get expectations under belief when I only have samples from belief bar? Which is exactly the same problem as we just talked about with importance sampling, right? I have a distribution P. I don't know how to sample from it. I have a distribution Q, which I have samples from it. How do I compute an expectation under belief when I only have samples from belief bar? Right. So as you'd expect, we're just going to divide P of X by Q of X, right? And so if you just divide them, you just get eta P ZT given XT, right? And so all we're going to do is we're just going to divide this and this, right? Cancels, right? And all you're going to get is P of ZT given XT normalized, right? And so the important thing here is that if I ever want to, I don't need to have samples from belief. I just need to have samples from belief bar, and I can still get an expectation under belief if I have weights, right? And so the reason we computed weights, which was this eta P of ZT given XT, is because when I want to compute the expectation, I just take a bunch of values, I compute the Fs, and then I compute the P over Qs, which in our case is going to be this eta P of ZT given XT, and then I take a weighted sum, right? And so the way the particle filter is going to work is that I'm going to have a list of states. I'm going to have a list of weights. And if I ever want to compute the average under a belief distribution, I'm just going to do a weighted average, right? And the list of weights is literally the importance weights. You don't actually need importance sampling. It's just a way to like understand the concept, right? But you're just going to have the list of weights. And if you ever want to compute an average, do like the sum of Wi f of Si summed up over I. That's it, right? Okay, so I think an importance sampling is a cool idea that goes far beyond robotics. It's applied in lots of other domains. But the key idea being, if I ever want to sample from Q, if I want to take expectation under P, I only have samples under Q. You just need to do reweighting. We can show that if P is the belief, Q is the belief bar, then the importance weights exactly compute to those like weights we compute on the particles. Right? The detour, but I think it's kind of cool. Okay, so going back to our particle filter, right? We're gonna essentially have the previous step gave us a list of states which was belief bar. For our measurement step, we're just going to compute these weights, which is going to be P of Z given X divided by the sum of P of Z given X. And that's going to help us incorporate our measurement, right? And so in some ways, just like we did in our like abstract example, we're gonna have like the belief speak, but instead of the states moving, we're gonna have the weights speaking, right? So like the states are going to be where they are. Like the measurement step never moves the states. The only thing the measurement step is going to do is it's going to change the weights. Right? Does that make sense to everyone? So the motion step moves the states, the measurement step changes the weights. And the weights carry over in the movement step, right? And so like you're just going to keep multiplying the weights with each other. Right? So you're going to keep multiplying, like let's say you have like states 1 to state n, and you're going to have like some set of weights. The next time you're just going to take the previous weights and multiply it. Right? So weights are going to keep multiplying. So the motion step moves the states, leaves the weights unchanged. The measurement step changes the weights, leaves the states unchanged. Right? So if you have two parts of a data structure, one moves at a time, and then the other moves. One moves and the other moves. Okay. You asked a question about what happens if the weights go to 0, right? Like, so one of the issues that happens in the particle filter, which we'll discuss, is if the weights keep getting multiplied and the measurement step doesn't really move the states, then you have lots of things that have 0 weight. And then you're like wasting a lot of particles, right? And so what we're going to do next is try to address that problem. Okay, but the way to think of the measurement step pictorially is after belief to belief bar, we've got a set of states, right? Then you multiply them all, or you multiply the weights, not the states, You multiply the weights by P of Z given X and renormalized. And so now the size of the circles is like the weights, right? So you see that the circle positions didn't move. Circles are in the same exact positions, just the size changed, which means the weights changed. Right? And so you just reweigh particles according to the measurement length. Okay, so let's run through an example to make this a little more concrete. Right, so let's say your belief is currently this. Okay, you have like 3 particles, and your 3 particles are the top particle has weight 0.5, bottom particles have weight 0.25, 0.25. That's your current belief state. You have 3 particles in those 3 states and those 3 weights. Then you're going to take a step forward with your motion model. Let's say your car went to the right. Okay, you're going to take a step forward with your motion model, which means that you're going to move the states. Right, so you're going to move the states to the right. So you see this one moves to here, this one moves to here, this one moves to here. But the weights remain exactly the same. Right? So there's the motion step. You're going to take every particle, stick it through the motion model, move it forward. Right? And then you're going to take a measurement. Right? So your measurement is like, I'm going to shoot a LiDAR out. I'm going to get some reading saying that I got a wall. Right? Like I'm going to get a reading that comes back short. It says there's a wall in front of me. So, then I take the likelihood of P of wall given state 1, P of wall given state 2, P of wall given state 3. Okay? Yeah? There's P of Z given X. This is P of C given X. So if you look at these likelihoods, the likelihood of getting a wall here is 0.02. It's very unlikely there's a wall in front of you if you were there. The likelihood of getting a wall here is pretty high. Like there's likely to be a wall. And the likelihood of getting a wall here is a bit higher than here, but not that high, right? And so what I'm going to do is I'm going to multiply the previous weights by this new P of Z given X, right? As I said before, you take the previous weights and multiply by P of Z given X. Yeah. So P of Z given X is going to be 0.02, 0.2, or 0.08, right? And then I'm going to multiply them, and then I'm going to renormalize them. So I'm going to multiply them. I'm going to get these numbers. These don't sum up to 1. So I'm going to renormalize them so they do sum up to 1. So, but now it's like kind of got a nice intuitive meaning, right? So we started with, this is the likelihood, 0.5, 0.25, 0.25. I moved, the belief state moved, then I got a measurement, and now my weights reflect the likelihood of where I am, right? So I still have 3 particles, right? Still have 3 particles, but the weight on the middle particle is way higher, which means that it's more likely. Okay? And so now I can just keep repeating this. So remember that like in the motion step, you move the states, not the weights. In the measurement step, you move the weights and not the states. Okay. Alrighty. So the overall particle filter algorithm, the first version, is you're going to sample particles from the motion model to move it forward, keeping the weights the same. And in the measurement step, you're going to multiply all the weights by P of Z given X and renormalize. And then you will repeat. Okay. And what you'll end up with is a weighted list of states and particles, or states and weights. And every particle is a combination of a state and a weight. Okay. Does that kind of make sense? Right? And there's a big issue. Remind me of your name? Isaac. Like you just pointed out, there's like a big issue with the weights often going to 0, which we'll address, but this is a valid version of the algorithm. You should try it on the homework and see if it works well or not. Okay, so as you pointed out, one of the challenges with like just carrying along weights and just keep continuing to multiply them is right, even at this state, you saw that like the weights became way sharper. Right? They went from 0.5, 0.25, 0.25 to something that's sharper. And the more you go along, like the more it's going to get like peaked. Some weights are going to get really high and some weights are going to get low. Right? And so the challenge becomes that if I like keep multiplying these weights at every time step, it becomes numerically unstable. And many of the particles go to 0 weight and you're wasting a lot of particles where there's no likelihood. And so the challenge here is that one is that you blow up and get numerically unstable. And two is that you like are wasting a lot of particles. Like the states that like they have lots of particles which have really low weight in states that are very unlikely, right? And so we need to find a way to like avoid this like high concentration of weight in a few particles, right? And so the way to kind of think of it intuitively is let's go back to this example, right? Like you can see in this example, when you take a measurement, the particles are actually moving, right? The particles are moving to be closer to the things that matter. But imagine if I just had reweighting, like the only particles that have actual weight are the ones that are near the robot, but the rest of them I'm still wasting my compute and memory on them, even though they have really little weights, right? And so the whole point of the particle filter was not to waste compute and memory. So why are we wasting compute and memory? So um, the question we're going to ask next is the motion step moves the particles, the measurement step reweights the particles, but the weights, when multiplied over and over and over, will go to zero. Is there a way for us to move the particles in the measurement step also? Right? So we're not just wasting particles. So if the weights start getting imbalanced, can we move the particles over from the things that don't matter to the things that do matter? Right? So we don't waste compute and memory. So that's going to be the question of resampling. And so we're going to introduce this idea of resampling, which is trying to which is essentially trying to move the particles in the measurement step. So the motion step moves the particles, the measurement step reweights them. We're going to add resampling. Resampling is going to rearrange the particles in the measurement step. And that's going to like prevent particle wastage. Okay, so the problem of resampling is essentially saying I have a set of n weighted particles. So n weighted particles means that I have like n different states, and for every state I have some weight, right? So let's call those states SI, and let's call the weights WI, right? And so I'm going to say I want to like resample from this, and essentially like if I define this distribution, S1, 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 S2, blah, 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 and weights W1, W2, W3, like this defines a probability distribution, right? Like the weights tell you how much probability there is per particle. What I want to do is I want to like resample from this distribution so that I don't need to have the weights anymore, but I have something that's unweighted, right? But like calculates the same expectation. So I want to move the particles from things that are low weights to things that are high weights. And so essentially, what we're going to try and do, we're going to say this like set of weights represents a probability distribution, and we're just going to redraw n samples from that probability distribution. Right. And so if we redraw n samples from the probability distribution, we'll have more samples in the high likelihood places and less samples in the low likelihood places, right? And so the really nice intuitive way of thinking about this is imagine that you had a roulette wheel, right? And so the roulette wheel is basically representing like the circumference of the roulette wheel is representing the different particles you might have, right? And like let's say every like the every particle represents like one chunk of this, right? These are different particles, and the length of the circumference arc is proportional to like your weight, right? So like if you have higher weight, you have more of the arc, and if you have lower weight, you have less of the arc, right? And now we're just going to spin the roulette wheel n times, and we're just going to like choose the particles that it reached. So right, we're going to spin the roulette wheel n times, and so we're going to say, okay, we like spun it, and it reached the part of the circumference which is W3. So I'm going to pick one of particle 3. I'm going to spin it again, and it reached something which is Wn. I'm going to add one of the like particle n, right? I'm going to repeat this n times, and then I'm going to get n new particles, right? So if I have like a weight distribution, you can kind of think of this as like W1, W2, W3, etc. I can say like I'm going to think of this as on a line, right? So imagine that let's take an example where I had 3 particles, right? The first particle had a weight 1 over 8. The second particle had a weight 5 over 8. The third particle had a weight 2 over 8. Okay, we have 3 particles. Now I want to redraw samples. So I'm essentially going to think of them. You can do a roulette wheel, you can do a line, it's kind of the same. But I'm just going to draw a random number between 0 and 1. Okay, so if I'm going to draw a random number between 0 and 1, let's say it's like landed up here, I'm just going to take one of this particle, right? Let's say I sampled again. Let's say again it landed up here. I'm going to take another of this particle. Let's say I sampled again, maybe with some likelihood it'll land up here. So I'll take one of this particle, right? But you can kind of see, like, as you sample more and more and more, like the things that have higher likelihood will get more samples, and the things that have lower likelihood will get less samples, right? And so the point is that earlier we had a set of particles. Let's say I had like, 10 particles over here, but they were like really low weight, right? And I only had like some particles over here, which were really high weight. I'm going to move a lot more of the particles to the things that have higher weight. Right? And so, sorry. So the way to kind of implement it is you're just going to draw a random number between 0 and 1. You're going to divide the number between 0 and 1 to the the splits according to the weights. The weights all sum up to 1, right? And then you're going to draw a number between 0 and 1 and see which of the buckets it falls into, right? You can think of each of the weights defining a bucket. You draw these random numbers. You can see 0.97 falls into that bucket, 0.26 falls into this bucket, 0.72 falls into this bucket. And so you get a new set of particles. And the nice thing is you can resample as many times as you want. If you want to put more samples in, you can, right? But we went from a weighted set of particles to an unweighted set of particles. And so essentially, imagine like this was our distribution after the weighting. When you do resampling, you're going to like draw things from this roulette wheel, and then you're going to have like repeats of the particles. Right? So imagine that some particles at high weight. So like, for instance, this particle is high weight, and that particle is high weight. I'm going to have two of this, or I'm going to have two of that, right? And some particles that are really low likelihood, I just will not draw any samples from them. So like these guys disappear, and I have more likelihood, or more particles in the places where I have more likelihood. So Aaron, I think you asked a question last class of why would I ever have duplicate particles? When you do resampling, you would have duplicate particles because you can have more than one thing picking the same particle, right? Because you're resampling. Okay. So just to reiterate, we're starting from a set of like bunch of weighted particles, and we're resampling by just drawing from this roulette wheel or this line n times till we have a set of unweighted particles, but they represent the same distribution. Right? They represent the same distribution, it's just the weights don't keep blowing up, and the states are closer to things that we actually care about. Yeah. So the important thing here is now, like, if you remember our previous data structure, we had like S1 to Sn, we had W1 to Wn, right? In the measurement step, we are still going to compute Ws. But before going to the next motion step, we're going to perform an additional step of resampling. And in the resampling step, we're going to take these Ws, we're going to spin the roulette wheel a bunch, and it's going to change the S's. Like it's not going to be the same S's. I'm going to reshuffle the S's to be more in higher likelihood things and less in lower likelihood things, right? And so you're going to add an additional step to your particle filter. You're going to have the motion step, you're going to have the observation step, and you're going to have the resampling step. Then you repeat, right? 3 steps. Yeah. All the way back to 1. Beautiful. And that kind of prevents your like weight blow up. So the fancy name for this in the literature is sequential Monte Carlo. If you're interested, just look up sequential Monte Carlo. It's a cool body of work. But let's go through an example and see what resampling looks like, right? So we did the previous step. We got to 0.125, 0.625, 0.25. That was our likelihood. Now we're going to do resampling, right? So we're going to like put these on a line, draw a bunch of samples from 0 to 1, right? And so our numbers, let's say, were 0.97, 0.26, 0.72, right? So it's going to put one sample here. It's going to put 2 samples here, right? And so after this, our new distribution is going to be unweighted again. It's going to have uniform weights, but it's going to have 2 particles here and 1 particle here and no particle here, right? And so I like concentrated my belief away from things that didn't matter. And the weight was really low there, it didn't matter, so I concentrated my belief away from it. That's how the resampling step works, right? Yeah.
the particles rather than just removing the particles from releasing the weight?
Oh, because you're trying to keep the same probability distribution. So you're trying to still say like, I'm going to sample, it's like you're trying to sample things that are proportional. So it's not that like, it's not like 0.125 is zero likelihood. It's just less likely, right? So if you just remove the things that are low likelihood, then you're like setting their weights. Then you're setting their likelihood to zero, right? Whereas if I'm sampling, then I'm saying there's like still some chance of getting that particle. So like imagine that I didn't draw 3 numbers, I drew like 100 numbers. There'd still be some particles in the first one, but not zero. Whereas if we did the removing of the minimum, it would be like straight up zero. Right? So you want to keep some likelihood because there might still like my belief is not like zero there. Right? And so you want the particles to be representative. And so one of the pitfalls, if you look at this current number, we only have 3 particles and we only resampled 3 times, is that I like completely erased my belief on the top. Right? And so that's why you often want to be careful in how many particles you have and how much you resample. Those particles can disappear if you don't sample enough. Good question. Okay, so this is actually an example from one of Dieter's old projects on museum navigation. You can see that you're like going around and casting your LiDAR, and your particles quickly collapse to like where you actually are, right? So you're just like it's useful to look at this from the starting. So your uniform belief, then you made you did a motion step, or then you did a measurement step. And you can see that the measurement step is not unique. Your belief has not collapsed to zero. Right? You still have like some uncertainty in different places. And then you do a motion step, moves your belief, and then you do another measurement step, and your belief collapses again. Right? So like within a few measurements, your belief collapses. So that's how you'd expect your particle filter to work. So to recap the algorithm, you start from an initial prior, you do the motion step, take the particles, you move them, carry over the weights. You then do the measurement step, which is weight particles by P of z given x, renormalize. But before you go back to the motion step, you reweight, you resample the particles to get a new set of unweighted particles, and you right? And so that's how your particle filter is going to look like in the homework. You add this additional step of resample. And the idea is that you keep samples from the same probability distribution. You just don't carry along these weights that blow up. And you're not wasting particles where there's no likelihood. Okay. So how are we doing on time? Okay. Maybe real quick, if we can take 2 more minutes. Some of the challenges with particle filtering are that is the resampling step, like you kind of alluded to, like some of the particles disappear, right? And so imagine that we have this case where you have 6 particles. They're equal between 2 rooms. There's no motion, there's no observation. I just keep resampling from the same distribution. I have 6 particles, 50-50, right? They have equal weight, and I'm just going to keep resampling from this distribution, spin the roulette wheel a bunch. Will they remain 50-50? No, right? Like if you're probably it's like a binomial, it's like you're flipping coins. And the likelihood that you get exactly 4 coins in each or 3 coins in each is going to be around 30%. And so you'll see that like, after some resampling, you'll get it to be like 30%. That 30% will become like 10% and smaller and smaller and smaller. Eventually, you'll see that like the particles will all migrate to one room. And if I have infinite samples, this is different. But if I have finite samples, right, the particles all migrate to one room. And so if you over resample, you'll get the particle balance becomes like our particles become imbalanced. And so there's often an issue called particle starvation, right? And so your particles are like starved from room 1. If you just resample too much, the particles go start becoming imbalanced. And so the challenge here is that you want to like avoid over resampling. And so the simplest solution to this is just resample less, right? Like for instance, if your particles are pretty uniform, don't resample. Right? If your particles are really imbalanced, then it's good to resample because you don't want weight wasted. Right? But if your particles are close to uniform, like all the weights are equal, they're high entropy, the ratio of min to max is low, right? In all of those cases, you don't have to resample. Just keep the weights around. Right? But you can kind of, the easy way to think about the resampling step is like, imagine I had a list of particles and a lot of the weights were 0. Like, why am I wasting compute on things that are zero weight, right? So in that case, you want to resample. But if all the weights are kind of meaningful, then it's fine to keep them around. And so you don't have to resample all the time. And we will talk about this next time. It'll take a little more time, but maybe the important thing to remember is just this figure of particle filtering, right? Motion step, waiting, resampling, repeat. Okay. See you Monday.